Yes, good. So I would actually love to attend this event in person, but unfortunately the situation is such that I'm only able to present virtually. So, but still I'm grateful for the event organizers for inviting me to attend. And today I'm going to deliver a talk on the application of CT, which all of you I think are familiar with, to laser flash analysis. So CT is used here as a tool to cross-validate and verify the LFA measurements that we get experimentally. And other people have also contributed to this work. So this is Fabien Leonard from the University of Manchester, my colleague Alex Laurer from NEC Gerätebau, and Vadim Zborovsky from the Lebedev Physical Institute. So the background for this work is to actually prove that the LFA may be a suitable tool to study porous materials. The LFA is actually a thermophysical method which is based on the Fourier law. So all thermophysical methods, at least all the conventional methods, are based on the Fourier law, which says that the heat flux is linearly proportional to the temperature gradient. And the question that we posed here is, can heat conduction in a porous solid be reduced to a 1D problem? So basically you have the sample for the laser flash analysis, which usually comes in simple shapes like cylinders. And obviously when you deal with porous samples, they have very complex microgeometry which is formed by the interconnected pores and the matrix. And the question is whether we can actually propose an effective medium sample which shows the same temperature behavior as the more complex and more detailed 3D representation. But it's actually more simple to quantify something that is geometrically less detailed. And obviously we have used the LFA tool produced by NEC, because NEC is perhaps some of you know that NEC is the world leading manufacturing company that produces different kinds of thermophysical instruments, and the LFA 457 is one of them. So it works on utilizing a neodymium glass laser, which has a wavelength of about 1 micrometer. So this laser hits a sample, which is placed inside a gas chamber. Then there's a short period of light absorption in the sample. And when the light is absorbed, usually at the sample front surface, we can track the propagation of the temperature front by taking measurements using an infrared detector. So usually indium antimonide detector. And the samples used in this work were kindly provided by Exantis, and they have been produced from a aluminium magnesium silicon alloy with a fixed porosity of 60%. But the different samples that we actually measured, they had different size distributions of the pores. So we focused on small, medium, and large pores. And in order to also get the accurate geometrical representation of those samples, we used the CT, the micro CT available at the University of Manchester, and my colleague Fabien Leonard has kindly provided his assistance to actually measure those samples. I mean, to construct the meshes on those samples. So I'd like to start just by introducing the conventional paradigm in laser flash analysis. So whenever you have a conventional LFA experiment, you have the material which you want to measure. So you're looking at some thermophysical properties of the material. Basically, most often you're looking at the thermal diffusivity of the material. And you put the sample, which is made of this material, into the LFA chamber, onto the sample holder. You activate the laser, which hits the sample. The light is absorbed, and then you track the heat transfer, and you get the time temperature profile using the detector. So it's a time sequence of the so-called brightness temperature values. And so in order to deduce the thermal diffusivity and other properties of the sample, you have to solve the inverse problem of heat transfer. And in this case, basically, this problem is quite simple. It is shown in the right corner of this slide at the bottom. So basically, in this representation, it's a one-dimensional problem where you have a distributed light absorption reflected by this additional source term in the equation, and you also have the heat losses due to radiation or convection at the rear and front surfaces. Of course, you could also propose some two-dimensional models, but it doesn't really play a vital role in increasing the accuracy, because the flash is usually of the same size as the sample's diameter, so 12.5 millimeters. And the problem with this setup when we are dealing with porous samples is that classical LFA, which has been formulated more than 50 years ago, requires homogeneous samples. But obviously, when you deal with porous samples, they are heterogeneous, and they combine two phases, the porous and the matrix. So if we assume that the microgeometry only changes the thermal diffusivity value, then we can actually say that there is an effective medium which has the same time temperature output as compared to the more complex geometry, but this effective thermal diffusivity actually corresponds to this this complex geometry. And this has been proposed as the hypothesis for this work. So we tested this hypothesis. And then we started with acquiring the time temperature data using the LFA instrument, and we did this starting with 10 millimeter samples. Usually LFA samples are much smaller, but because you have open porosity and you don't have anything like any coating, we didn't use that because when you introduce some coating, then you actually introduce a third phase, which can jeopardize your measurements. So we just use like a simple open porosity sample, placed it into the LFA, and measured it measured it for measured different samples corresponding to small, medium, and large pores. And you can see that actually the raw data, which is shown on this slide, it actually shows a good signal-to-noise ratio. So it should be a no-brainer to actually come up with the thermal diffusivity values, because speaking just from the point of view of optimization, this is not a very complex problem. And you can actually see that the solid lines which are visible on this slide, they correspond to the solution of the inverse problem. So they actually fit very well. They actually fit this data very well. So then when you look at the temperature dependence of the thermal diffusivity for different samples, you can see that the thermal diffusivity of porous samples changes depending on the size distribution of the porosity. But then we discovered we discovered a problem with those measurements. The problem consists in the size dependence of thermal diffusivity. So if you take different samples that have different thicknesses but the same diameter, so you can actually come up with very different values of thermal diffusivity. And this was not right, because if you have the same material, then no matter what the sample thickness is, you must get the same value of thermal diffusivity. So either the Fourier law breaks down, or you don't know how to do the experiment, or well, maybe there's a, I don't know, a divine intervention or something like that, which prevents you from measuring samples. And then we also produced samples with closed porosity on the surface. So we did this by grinding the faces of those samples. And because this alloy was actually very ductile, this produced opaque surfaces. So we also compared those measurements with the open porosity measurements, and we discovered that there's a difference in thermal diffusivity of the closed porosity and the open porosity samples. So a different paradigm which we proposed to use was to implement the cross-validation with a virtual representation of the LFA experiment. So basically a digital twin. When you operate with a mesh that you can measure with the CT, you implement a ray casting algorithm to simulate the light absorption, and then you do the conventional finite element analysis, and you compare those results with the physical twin. So as I said earlier, the CT was done at Manchester University. The various parameters are shown on this slide. So a voxel size of 9.71 micrometers was used, and the meshing was done in the Viso software. And later we also quantified the mesh parameters using the VTK software. So the meshes consisted of 4 nodal tetrahedral elements, and we can actually see that the mesh quality is reasonable. The inverse aspect ratio is about 2. So, well, it's not perfect, but at least it's okay. And the typical edge length of the element is smaller than the actual average pore diameter. So next we also, Fabienne helped us to analyze the pore size distribution and the actual distribution of the pores. This was done using 2 different approaches, the skeletonization and the sphere fitting, with sphere fitting showing better results in this case. And overall, we can actually see that the porosity distribution is more or less homogeneous. It corresponds to the nominal 60% as described by the manufacturer, and the average pore diameters are also approximately in line with the nominal pore size that has been given to us by the manufacturer. So when we're dealing with porous materials, we actually have tortuosity, right? So porous materials are tortuous in the sense that the thermal wave, which starts to travel through the matrix, it actually does not travel a straight path, but it follows a complex curved path, which is greater than the B line between 2 points. So in order to quantify this, we used different methods. For example, the centroid path method available in the Viso, and also the geodesic versus Euclidean distance maps. And we got different results. And it seemed that after comparing those results with our data, these distance maps produced the most reliable tortuosity data that we got. So next, we also used a certain algorithm which we developed specifically to determine the visible surfaces from the illuminated side and also from the detector side. So the algorithm is very simple. You identify the boundary between the matrix and the pores. Then you select the cells where the dot product for the between the direction of the laser beam and the normal to the surface of the face is positive. You cast a ray from the cell center towards the source direction, and you test this in the intersection of this ray with other surfaces using the Mueller-Trumbor algorithm. So you assume that side is illuminated if this test passes. Later, we have drawn histograms of the cumulative contribution of the area of those spaces to the actual visible faces, and this distribution is seen to fit the exponential the expected exponential function, which is given by the Beer-Lambert law. So later we used the heat problem statement, which is shown on this slide. This is a simple three-dimensional heat problem, but the only interesting thing here is that the boundary conditions are given both at the illuminated surfaces, where a rectangular pulse shape is assumed, and at other surfaces which are not illuminated, so they're not visible, the boundary conditions are just adiabatic. And of course, you also have to account that the detector also sees just a part, well, not just the surface faces, but it sees deeply into the samples. So it is able to combine the contribution of different faces that are visible. Right, and then later when you formulate this problem, it actually just boils down to solving a sparse linear system of equations, which is, you know, fairly simple. And in order to solve this, because there's a lot of equations that you have to use, you have to solve. We just implemented the Intel MKL Paradiso package using multi-core shared memory system, and we also implemented we have taken the advantage of the linearity of the problem, and this has actually facilitated the calculations very much, because the factorization for the matrix can only be done at the first time step, and then you only need to do subsequent factorization just when you change the time step. So in total, you have 5 factorizations, and you can actually accomplish calculations with meshes corresponding to those samples in maybe a day or a few days, using the Google virtual machine instances which we used in this work. So here you can actually see some nice animations of the actual temperature propagation in samples with different size distributions of porosity. And you can see that, for example, in the large pore samples, it seems that there are some hot spots forming at the front surface, at the top surface, which is illuminated by the laser. And it appears to be like when you decrease the size of the pores, it appears that you have a more homogeneous heat front, which is moving across your sample. So this has been visualized in ParView, which is a nice tool for visualization. And then we compare the actual time temperature profiles that we have in the experiment, in the LFA experiment, with the time temperature profiles that had been simulated in the CT-FEA approach. And you can actually see that the thermal diffusivity is in, I would say, a good agreement between those two approaches. So for example, the same variation in thermal diffusivity for pores that have different size distributions is reproduced both in LFA and FEA. Although I must say that the gamma factor, which reflects the let's say the light absorption profile, this is the gamma factor in the Beer-Lambert law. This is quite different. So this was surprising for us. And when we compared the prediction that we have from the from the inverse problem, here you can deduce the gamma factor as the calculated parameter from the inverse problem by just adjusting optimizing the parameters, the four different parameters that you have for the macro scale heat conduction, where you assume that you have a homogeneous sample, and then you just have four parameters including gamma, and then you try to vary them and select the best fit in case of the to fit the actual FEA data. Then you can actually see that the gamma shown in blue here is very different from the gamma, from the real gamma that corresponds to light absorption. So this has led us to believe that there is some kind of model mimicry taking place in this case. Later, we also compared the results of the closed surface pores and the open pores using the different tortuosity corrections. And still, even when you correct for tortuosity, there seems to be still a difference between the two approaches. So something was not right. And actually, when we try to fit the data that we had from FEA for the samples with closed porosity, we actually discovered that there is a time lag in the time temperature profiles. And it's so hard to identify that it usually leads to estimating to arriving at the wrong estimate of the gamma parameter. And if you introduce a fake gamma parameter, that if you introduce a fake absorption profile, then you get the same time lag of the time temperature profile, but it's not really true. So it's like the model that you're using is just producing this best fit just accidentally. So therefore, we think that we have proven that the Fourier law breaks on macro scale for these metal foam samples. And just to summarize everything that I have said previously, so if direct CT-informed FEA calculations are possible, they should be given priority over misinformed LFA experiments. And existing coarse-grained models fail to describe temperature transients in metal foams. This leads to the size dependence in LFA measurements. And the Fourier law is therefore not strictly applicable to porous media. Effective medium models still needed to validate complex installations combining multiple levels of details. And I would like to take time to thank my co-authors who are presented on this slide. And also, if you're interested in this topic, there are clickable links on this presentation, which I hope will be available after the event is over, and perhaps you can navigate through them. And there are also some other examples of the misconceptions in, let's say, in the laser flash analysis that few people pay attention to. So I think that I'm now ready to answer your questions if you have any, and I'm gonna stop sharing my screen.
Thank you, Artem.